Good afternoon, student of the course 4006. Here we are with our work that we are doing on partial fraction and how can we use that tool to get kind of these integrals which they seems very hard to deal with, but using the technique of partial fraction we can simplify to the point that they are very easy to deal with. Now, when you take a look to an integral like this, as always, you check how they look, how the numerator looks like. So it looks like a polynomial. And how about the denominator as well? They look like a polynomial as well. Now, the question is whether the denominator has been factorized. And the nice things about this kind of problem, like for example on this one, the denominator looks like it has been factorized. So when you, in other words, let's say that this type of integral is of the form of, let's say, px, well, actually, let's do it different. Uh, qx over px dx. So we are integrating that. The thing here is to look px and find out whether px has been factorized or not. It is a polynomial. The question is, has been factorized? And in this case, the answer is yes, because it's being presented in this way: x minus 2, x plus 1 to the cube. So it has been factorized enough that, therefore, in your head, you might be thinking, well, can I benefit if I use partial fraction? And the answer is maybe. It depends of the order of the denominator versus the order of the numerator. In this particular case, the order of the numerator is 2. The order of the denominator, this is x to the cube eventually, and there's an x here, so the order of the denominator will be 4. So the difference here is 4 minus 2, that's 2 positive, meaning that this is truly a fraction. You don't have to do long division of anything like that. Second thing is already factorized. What that means is that you can definitely get the roots from here. And for example, you can have a root here, x equal 2, that would be a root of that denominator. And definitely you have a root which said x plus 1, that means that x being equal minus 1, that would be actually a root as well of this function called px. So when you look at this, basically it has everything right just to do partial fraction. Now, the only thing that now that we need to consider is that this is not the regular case 1. Remember, case 1, and let's put it somewhere here, case 1 of partial fraction is when px is a linear function of, let's say, when you factorize of something that looks like this, x plus plus minus a, just to say the least, and then you have another expansion or another factor, let's say x plus minus b plus another one, x plus minus c, and so forth. So they are linear expansion. So that will be case 1. Now, case 2, the case, this issue about case 2 is when you have px, but now px, some of these linear expansion, let's say that you have these, but then all of the sudden the second one here is not linear. It's to the second, to the third power. Let's put to the second. You see, that is case 2 of partial fraction, and that's what I'm trying to, so that you understand that the differences between case 1 and case 2 is that one of these expansion is to a power above 1, 2, 3, 4, and so forth. So in order to apply partial fraction to this function here, we need to expand that as following. Like say, hey, x2 minus 2 over x minus 2 x plus 1 to the cube. If I expand that, that will be a over the first linear factor, that will be x minus 2. But now, careful here. So you will have another expansion, will be another fraction, will be b over x plus 1. And you repeat, you see, until you get to the third power, which is shown there. Oops, close this too much. And then that would be d over x plus 1 to the cube. See? And that's the big difference between, again, this is case 2. On case 1, probably if you only have two linear factors, that will be over a over that one of the first expansion or the one factor, and b over the second factor, and that would be it. But in this case, you have this x plus 1 to the cube, meaning that you will expand in partial fraction as shown here. The next step is you need to multiply the whole thing, you know, like we did in case 1. You multiply by the denominator here, and when you do that, you end up with something like this. X squared minus 2 equal a. Now, I have the x minus 2 here, x minus 2 here, so that cancel out. So the only thing left is the x plus 1 to the cube. In the case of b, I end up with the x minus 2, but I also end up with x plus 1 square, because this is to the cube, but this is 1 here. So now, what about c? C end up with x minus 2, but it also end up with x plus 1. And what happened with the d? Plus d time x plus 1 to the cube, x plus 1 to the cube cancel out, so you end up with x minus 2. And that's basically it. So you have expanded and you are ready now to look for A, B, and C, and D. And the trick here is to find out what what value of x you could use that will eliminate most of the variables except for one. Like, for example, definitely you see the x minus 2 here, x minus 2 here, x minus 2 here. So if I set that x equal to, the b disappear, the c disappear, and so the d disappear. So the only thing that is left is the letter a. So that means when x equals 2, that would be 4 minus 2 equal a. Again, with the x is 2, that would be 2 plus 1, that would be 3 to the 3. So the result is that the letter a, or that value, will be equal 2 divided over 27. See? That's the value of a. And one thing that you have to remember is that this integral looks difficult, but when you expand that integral in all these terms, basically what you're looking at is that you are breaking the integral. This is very complicated at the beginning like this, but you are breaking that integral in a small fraction like this one, this one, this one, and this one. So the first two are definitely logarithm, the first two. The third one, the third one and the fourth one are different. Probably more familiar to, I would say this is more familiar to when you are doing these two integrals, the third one and the fourth one here are more familiar to this integral, x to the n. These two will end up looking more into that, and we'll see that in a second. So, but the first two, this one and this one, are definitely logarithm. Okay, so watch for that. That's the only thing that you have to be careful. Now, I found what is a. 227. I can complete this very easily. How about, let's see if we can find something else by doing that, uh, by picking the right value of x. For example, what happens if I pick x minus 1? Okay, so if I pick x equal minus 1, let's see what disappear. Minus 1 disappear the a, minus 1 the b, minus 1 the c, and the only thing is left is the d. Excellent. So that means minus 1 squared, that's still 1 positive, minus 2, that would be minus 1, equal, and the only thing that is left is the d. So that would be d times minus 1 minus 2. So d for this problem will be minus 1 over minus 3. So that would be 1/3. And we got the d. So basically A and D, sorry for that, A and D can be solved already. We can solve this part here, and we can solve this one. But let's find out what is B and C so that we get this going. Now, let's see if I can close this more. We are back here, and now I think that we either pick x equal 2, x equal minus 1. I think that I'm out of option now for how can I get the B and the C. When that happens, you can still do very good. Like for example, how about if I pick x equals 0? You know, pick numbers that make your math easier. If x equals 0, then you will have a function. I mean, you will end up with an equation, and then, like for example, pick another value, like when x equal 1. So you will generate another equation. With two equations, basically that means that you have to solve a simultaneous system, two variables and two equations. So let's do that. So when x equals 0, if I go back here, let's put it here so that I don't, x equals 0, what happened with my function? I end up with minus 2 with x equals 0 is minus 2. Now we have here equal a, when x is 0, that will be 1 to the cube. That's still 1. I write it there. And then plus b. Now here, when x is 0, that means minus 2. And that would be 1 squared plus c. And the c will be when x is 0 minus 2 plus 1. I mean, multiplied by 1, x plus 1, that would be 1, plus d multiplied by x, but x is 0, that would be minus 2. All right, so let's simplify this equation a little bit more. So that means minus 2 equal a. What happened here? You have minus 2b. You have here minus 2c. And you have here minus 2d. Now, I have the values already for the a. So that means minus 2 equal 2 over 27 minus 2b. B is not there, so I put the b here. Minus the c is, I don't have that value yet, but I do have the value of d. The value of d is 2 multiplied by 1/3. There we go. So basically, if I move all this back here, so I have minus 2 over 27 minus 2/3 plus 2/3, sorry for that. This go back here. So this go negative and this go positive. So I end up with basically minus 2b minus 2c. All right. So if I simplify this first equation, end up like, if I use 27 here, uh, that will be minus 2 times 27 minus 2, and here you have plus 27 times 2. If we do all that math there, hold for 1 second. So we got here 54 minus 2 plus 27 over 3. That would be 9. That would be 18. All that divided by 27, and that equal minus 2b minus 2c. So the final result here, when x, all this is when x equals 0, that will be minus 56. That will be 38 negative over 27 equal minus 2b minus 2c. If I multiply by minus 1, just to leave everything more clean, that will be 38 over 27 equal 2b positive plus 2c positive. Right. That's the first equation, and that's when x equals 0. You see, we cannot solve for any of them because I need another equation. Well, that's simple. If you get like, for example, let's copy all this so we don't lose track of it. Okay, when if I put it here somewhere, so we're gonna do now the particular case when x equal 1. Let's do that. When x equal 1, so we have 1 square, that would be 1 square minus 2, so that would be minus 1, and then we put the 1 here, and let's see what happens. So that would be a to the 1 and 1. That would be, remember, when x is 1. Okay, when x is 1, that would be 1 and 1. That would be 2 to the 3. Let's write the number. That would be 8. End of the story. All right, plus b. Now, let's see how b looks like. When x is 1, I will have a minus 1 here. And when x is 1, I will have 1 plus 1. That's 2. So that will be a 4. Plus c. When x is 1, I will have a minus 1. And when x is 1, I will have here a 2. D. When x is 1, I will have a minus 1. All right. So let's simplify this a little bit. Clean them up. That will be minus 1 equal this that is there. Now I have here minus 4b minus 2c minus d. Now let's use what we know, and what we know was that a is 2 over 27, so minus 1 equal a 2 over 27. It was positive or negative? No, positive. Good. And how about the d? The d is 1/3. So I end up with minus 4b minus 2c minus d, but d is 1/3. All right. So let's get all numbers in one side. So that will be minus 1 minus 16 over 27 plus 1/3 equal minus 4b minus 2c. Almost done. So if I use a common denominator, let's say 27 here, so I will end up with minus 27 here, minus 16, and that will be, again, 27 divided by 3, that will be 9, so that will be a positive 9 here, equal minus 4b minus 2c. 2c. So that would be minus 27 minus 16 plus 9. That's negative 34 over 27 equal minus 4b minus 2c. If I multiply by minus 1 both sides, so end up being 34 over 27 equal 4b plus 2c. So my other equation, which is somewhere here, I'm gonna copy this and put it nearby here. So I have those two equations to solve simultaneously, and that's the main point. As you can see, if I multiply by a negative and then add to the other one, you can eliminate the c very quickly and end up with the problem solving for b. You can also use, like for example, resolve for c on this equation and put it here, and then resolve for b. I mean, there's many techniques to solve simultaneous equation. You can use solver in Excel if you want to as well. But the simple thing is, they are so simple enough that you can multiply this by minus 1, and when you add that to this one, the 2c is gone. So you end up like minus 34 over 27 equal minus 4b plus minus 2c. If you add that to this number here, 38 over 27 equal 2b plus 2c. When you add those two together, so you end up like minus plus 4 over 27. Good that they have the same denominator. So 38 minus 34, that will give 4. And that's equal minus 4b and 2b, that's negative 2b. And the c is gone. So the result here is basically, let's fix this too. The result here is b equal 4 over 27 divided by 2 negative, and that would be 2 divided by 27 negative, and that's the result for b. Okay, so now we need to get c, and you can use any of the two equations, right? We need to solve for c, but we already know b. How about if I use this one here? Okay, let's do that. So that would be 38 divided by 27 equal 2 multiplied by b, but b is minus 2 over 27 plus 2c. If I solve now for c, that would be 38 over 27 plus this move down here, that would move positive 4 over 27 equal to c. That would be 42 over 27 equal to c, and eventually you divide by 2 and you get the final value of c. That would be 21 over 27. That if you simplify a little bit further, this divided by 9, by 3, if you divide by 3, that would be 21, so that would be 7, and 27 divided by 3, that would be 9. And that's also a valid result for C. So we got all the values. Let's see if I can make sense out of all this, because basically we get, the problem here is that this was long. You see, this was, so that end up having at least, C and D. So let's pick this. And let's get it here. Now, we need the value of A and we need the value of B. Value of A for this problem is 2 over 27. So I can certainly write it here. It is a constant, but let's say 2 over 27 dx, right? So, and let's get the value of b. Why I'm gonna go in order just because it makes sense to work this and this integral first, because they are logarithm. There's no big deal on these two integrals for this problem. B on this problem end up be, let's see if I got the b here, negative 2 over 27. Negative, interesting, right? One is positive and the other one's negative. Negative 2 over 27 dx. All right. Now that we are in this, let's get the c as well. C was 79 dx. How about the d? The d value was, see if I got it somewhere here. The d value going up. One third, the d value. So let's get now this big enough. So the d value was 1/3 dx. All right, so we are now ready to get this integral, which was very hard to deal with, but now is such a way that it's very simple. Like for example, the first one here, everybody will know that that's 2 over 27 times the logarithm of x minus 2. First, very good, very easy. Second one, negative 2 over 27. Now, here is again logarithm of x plus 1. Not a big deal. How about this one? This one is not logarithm. You have to understand that it's not, because the order of the denominator is 2 and the order above the numerator is 0. So that's not logarithm. And by the same token, the last one is not logarithm either, but it's belong to a simple family. So let's work the result of this one first. That one will be 7/9. I can take that out, the integral dx over x plus 1 square. To work that out is easy if you do a variable substitution and you leave x plus 1 equal u, so that the u is the dx, and then I think that is complete, is here. So this means that this integral is basically of this family. I can put here du over u. But that u, x plus 1, is square. Remember that. So that means that I have 7/9 the integral of u minus 2 du. But this is of that particular family that I told you. This is of the particular family of this type of integral. Right? So, and we all know that this is xn plus 1 over n plus 1. So that means that this integral is 7/9 over u minus 2, let's write it here, plus 1. And at the denominator I have the minus 2 plus 1, meaning that I have 7/9 u minus 1 over minus 1. See? So if I get now the what is u by definition is x plus 1. So this result will be negative 7/9 times x plus 1 minus 1 to the minus 1 power. Or the end of this result will be something like 7/9 over x plus 1. You can express it like that as well. And that's the result of that particular integral. So if I keep the order here, that would be plus, or I should put a minus better, minus 7/9 over x plus 1. And that will do. So that's the integral of this particular one. How about the last piece, this one here? Let's copy that. And let's work the same one down here. And that will be, oops, that will be the end of this. For that one, I mean, we can do the same trick. Remember, x plus 1 to the cube, and there's 1/3 here in front. So I can definitely use the change of variable, like, for example, u equal x plus 1, and the du is the dx. That's nice because I have a dx here, and there's nothing more here. So the 1/3 will come out, it's a constant. And then I have the integral of dx, but it's du over x plus 1, but that's u to the cube. And again, this is just happened that you can do this 1/3 the integral of u minus 3 du, and this again is of this type of family of integrals. So the solution here for this one is 1/3 u minus 3 plus 1 over minus 3 plus 1, and that will be 1/3 u minus 2 over minus 2. So the result here, minus 2 and this 3, that will be minus 6, 1/6 u minus 2. But if we recover what is the definition of u, which in this case is x plus 1, so our solution will be equal negative 1/6 1 over x plus 1 square, and that will be the solution, and this will be the solution for that final integral, which is this one here. Let's paste it here, and that go right there. See, I had then all the terms, all the integrals for this big and ugly integral end up being, this is the first part, second part, that's a logarithm, this third part, and finally this last part here, which since this is a general integral, it doesn't have any limits, so we put plus c here. And this is the end of all that. We just work what is called case 2 of partial fraction, and again, examine very closely that denominator to find out whether it's case 1 or case 2. And the nice thing is that when the whole thing is factorized like this, you are definitely in a very, very good shape. As I always said, be safe, whatever be your final destination. This concludes case 2. Bye.